cosine, because cosine looks just like this. This part of it would be one cycle of a cosine. So it's probably smart if I use the cosine one because I don't have to shift it left or right. It's already set here. Now, not everyone's strong at graphing these or coming up with equations for it. I'm going to understand that. We're not all going to get 100% of this. I'm going to show you the stuff you should get correct, though. This is stuff that anyone that can just take a second and look at it can get correct. The first thing you're going to do to start getting it correct is drawing what's called the sinusoidal axis. That is the line that runs smack through the center of it. What was that? Midline? Oh, okay. We can call it a midline, but officially it's called the sinusoidal axis. It's okay. Midline makes sense too because it goes through the middle. All right, just know where that line is. You don't have to memorize sinusoidal axis. It's what it's called, but I'm not testing you on that. Can you draw it? Sinusoidal. It's basically Sinusoidal. Okay, anyway, let's not get bogged down with this. Can we draw this line? Whatever you call it, can we draw that line? Now, the first thing I'm going to get from this line is, how did it get shifted? Did it go up or did it go down? Well, in this case, it went up 1 unit. That is going to be your K value. This value, up or down, is going to be your K value. So you should get that one down. The second one you should get from your midline is you should be able to get your amplitude. Your amplitude is your distance from your midline to either the top or the bottom. So I'll do that in purple. That will be this distance here. That is 1 unit. That is known as your amplitude. That is your amplitude. Your amplitude is your A value. So right now, I have 4 letters I have to fill in. I already know 2 of them just by drawing that midline. I have whether it got shifted up or down, and I have the amplitude. Unfortunately, in this example, they're both 1. That's where it can get a little confusing, but know which one goes where. Amplitude A, shift K. So, if I needed to write this equation, at the very least, I can go, oh, I know it's 1. I'm going to use cosine. I'm going to leave a blank for B because maybe I can't find that. Minus something. And then I have plus 1. I got half my numbers just by drawing a midline. That's half of it. Let's do the next easiest one. The next easiest one is what goes in here. This is how far left or for how right you went. I don't need to shift it left or right. It starts exactly where I think it should. If I decided to pick sine, let's say I went back in time and I decided to pick sine, and we'll talk about it in the next one as well. Sine starts on the midline and ends on the midline. This got shifted left pi over 4, so this would have to be a plus pi over 4 if I use sine. We'll do an example of that next. But because I chose cosine, which is the easier one, I'm going to go ahead and say I didn't shift it. So it's just 0, and we won't have that 0 in a second. The hardest one to get is your B value. The B value has to do with the period. I'm going to show you 2 ways to come up with it. One way works in certain situations. The other one will work in all situations. The first one is you got to count how many cycles it takes to get to 2 pi. So if I look at the red one, that's 1 cycle. If I continue that on, let me change my color up a little bit. I would have 2 cycles. I can get 2 cycles in 2 pi. That means my B value is 2. However many cycles it takes to get to 2 pi, that's your B value. So that's one way to do this to find out your B value is 2. Now, that doesn't always work because sometimes it's a weird, it's like 2.3 and you don't know how far it is. We could take an estimate, at least that's something, but if you want the exact value more mathematically, you need to figure out how long it takes to do 1 cycle. It's called the period. So I'm going to go ahead and I'm going to locate the period of this. That's how long does it take to do one cycle. Well, one cycle takes pi units. That is the period. All right, if my period is pi, we have a formula that says period equals 2 pi over b. In this case, I know the period is pi, so that's going to go in there. So I'm going to have pi equals 2 pi over b. We would multiply both sides by b, divide by pi, and you'd come up with b equals 2. I'm going to use that method if I can't count how many it takes to get to 2 pi. Either it's zoomed in too far, or it's just a weird number of them. So you can always get the period equal to 2 pi over b, solve for b, and you can get your b value being 2. Your question should be, do I have to write it just like this? No. More often than not, I would readjust this and write it as cosine 2x plus 1. I'll accept either one of those. I believe on the summative, I do ask you to name your transformations. So in this case, I would say it went up 1, amplitude of 1, period of pi. That would cover all my kind of transformation there, because it didn't go left or right. Now, the whole reason why you want to list your transformations is in case you have the equation wrong, I can give you some knowledge points for understanding the transformations. Okay? Now, our next one looks more like our summative question. Our summative question is going to be, you have to give me two equations. One in terms of cosine and one in terms of sine. And that's what we have here. So that way I don't get to pick which one I want to use. Well, the good thing is, whether it's sine or cosine, there's key things that will always be the same. We're going to draw our midline. Or if you want to be fancy, I guess, you call it a sinusoidal axis. Just for us fancy people, though. That'll get me two of my values. It gives me my shift. My shift is down 1, so it's minus 1. Your amplitude is only negative if you want to flip it, so leave your amplitude as positive as best you can. So our amplitude is from that midline to the tallest point. So that'll be that distance there. That will be 2. Here's the good thing. If I know nothing else, I can at least write both of my equations with the values I know. So I can say y equals, my amplitude is 2 times sine of, I didn't find that middle number yet. I didn't find that minus number yet. But I do have minus 1. And the same thing is going to work for cosine. Cosine equals my amplitude times cosine, some b value, x minus some number, and this is minus 1. If we can't tackle the whole problem, tackle what you can. Don't get overwhelmed by a problem. Don't go, I know Mr. Bateman gave me some weird thing about period equals 2 pi something. Don't worry about that. Just get the ones you know how to get. Let's go ahead, and this number is going to be the same in both of these two. That's our period. I said there's two ways to come up with that. One way is count how many cycles it takes to get to 2 pi. So what I'm going to do is I'm going to come down here. I'm going to look and say, okay, one full cycle looks like it's that. It takes exactly one cycle to get all the way to 2 pi, so your b value is 1. So your b value is 1 because it takes one cycle to get there. 1, 1. Or if you did the other method, you might have said, oh, you know what? The period, it's always good to at least know your period because I can ask that question. The period is 2 pi. That's some terrible drawing. So the period equals 2 pi. So you could have done that 2 pi equals 2 pi over b. You're going to come up with 1. So both of these are 1. So man, whether I know cosine or sine doesn't matter. I know 3 of the 4 numbers. I hope this doesn't confuse everyone. Most of the time you can just count how many cycles it is. This is just a backup in case you can't figure that out. All right, now, the only difference between sine and cosine is it shifted or not shifted? Remember, sine starts on your midline. So notice how this one starts on the midline? That means for sine, I'm not going to shift it left or right because I do have one full cycle right here. Let me highlight that in purple. So this is, like I just did, this is one sine wave. Oop, that's too far. It starts on the y-axis, so I don't need to shift it left or right. So my left or right is 0. So for sine, we're going to have x minus 0, or you might have just had x in there. So I don't need to shift it because we already start at the right point. Cosine, however, starts high. It starts above the sinusoidal axis. So when I'm looking at cosine, I got to figure out the first time it kind of starts high, so I'm going to start here. This is one cycle of cosine. So cosine got shifted right. So for cosine, I got shifted right, and this should be pi over 4. If we had it labeled, this would be pi over 4. It gets shifted right, pi over 4. So this is minus pi over 4.
Wouldn't it be pi over 2?
Yes, it should be pi over 2. I'm looking at the wrong one. Thank you. Yes. That should have been pi over 2. Thank you very much. I was looking at other stuff. All right, we have pi over 2. Questions on either one of those two? Remember, your job is not to be the perfectionist of perfectionists. Get the stuff you can. Get those 3 or 2 values you can. Don't just quit and get 0 points on it. Okay? Good? As a reminder, this is recorded, so if you miss something, you can just watch today's recording and you'll hear my voice and see all this stuff as well. All right. That's all I think we're going to do. If you would like me to collect yours, just go ahead and bring them up here if you want me to hold on to them. I think it's better if you keep them because you can study them, but I'm more than happy to hold on to them. Yeah. All right, real quick, did anyone have any homework questions that they would just like to see? Homework questions? They're important. If you have them, ask them. Okay. I did want to look at one of them. We already did like sine and stuff, so I do want to quickly look at 49. Real quick. 49 says locate all asymptotes and holes on the graph of this function. So we're going to go through this real quick. This is the homework that was due today. Now, in order to find holes and asymptotes, you need to factor the top and you need to factor the bottom. Now, the top is not completely a difference of squares, so all you could do to the top is turn this into 2 times x squared minus 8. On the bottom, if you factored it correctly, you should have came up with, let me just eyeball it, we should have had a -3 and a +2. So this isn't from today's, this is homework that was due today. So if you're looking for it, it was from yesterday's or the other day's lesson, and this is homework 49. All right, to locate a hole, you would need to have x minus 3 or x plus 2 on the top and bottom. We do not have that, where you can cross it out. So there are no holes. No holes. But there are going to be vertical asymptotes. Your vertical asymptotes are your x values that ruin your denominator. In other words, you can't have 0 in the denominator. So 3 would break this, and -2 would break this. So for vertical asymptotes, we'd have x equals 3 and -2. I do need that x equals, because it is a straight line. We can just use it once and put a comma. I understand what that means. Our horizontal asymptote, that is where I think we struggle a little bit. we need 3 rules for a horizontal asymptote. Your first rule is if your exponents are the same, you just compare your biggest exponents on your top to your biggest exponent on the bottom. If they are the same, which happens in this case, these are the same exponents. If they're the same, you divide your lead coefficient so the number's in front of it. So the number in front of x squared is 2. The number in front of x squared is 1. So our horizontal asymptote will be y equals 2 over 1 or just 2. I'm going to leave it as 2 over 1 because that's important for you to understand. If your exponents are the same, you divide your coefficients. If your exponent is bigger on the bottom, it's just y equals 0. No work needed. If your exponent is bigger on bottom, it's y equals 0. So if this was 2x minus 16 over x squared, I'd go, oh, it's just y equals 0 because your exponent's bigger on the bottom. If it's bigger on top, you probably didn't do so much with that. That was your slant asymptote. That doesn't show up as much. If you're not sure what to do, the best guess is y equals 0 if you're just guessing, because that shows up the most. Second most is you divide your lead coefficient. Your third most, or the least one, would be your slant asymptotes. Questions on that? That is on your summative. And I put nothing with slant asymptotes on it. No, I didn't. All right. We're going to quickly, because I want to do that first, we'll talk about this warm-up real quick. So suppose you invest $1,500 in a savings account and an annual interest rate of 4%. Write an equation to represent the amount of money you have after T years if it's compounded monthly. Now, any one of these functions, let's just call it function T, is going to be exponential. Compounding is always going to be exponential. Now, when you're compounding something, you need to have your first value. My first value is, I start with $1,500. Then we need some rate. I'm going to do this all wrong to start off with, but it's the good principle for this. So my rate is 4%. And I'm like, I got Mr. Papian. I'm not going to put 4 in there. I'm going to put the wrong equation at the beginning. So don't copy me for verbatim. It's 4%. And it's raised to some time. The first mistake I made is, if I multiply something by 0.04, I'm going to decrease it in value. That won't increase. How do I change that 0.04 so it actually increases in value and not just decreases? I have to add a 1 to it. So realistically, I should have said, okay, we're increasing, so that should be 1 plus 0.04 to the t. My t is in years, but I'm compounding it monthly. That means in 1 year, I want it to have compounded 12 times. Right now, if I plug in 1 in, it just happened once. So if I want it to happen more times than once, I have to multiply. So I do need to multiply this by 12. Now when I plug 1 in it, hey, it's going to happen 12 times in 1 year. 2, it's going to happen 24 times in 1 year. Now, this only works for compounding interest because banks are greedy. Banks aren't going to give you 0.04 each month. They're going to give you 0.04 in a year. So what they're going to do is they're going to take that 0.04 and they're going to divide it by how many times it actually got compounded. So I'm going to divide that by 12. This is unique to interest problems with money, that dividing it here. Good, bad, somewhere in the middle? Más o menos? Okay, today we're just learning some logarithm rules. We're going to learn a product rule, a quotient rule, and the power rule. All of these are used to manipulate a logarithm to look slightly different. We call it either expanding or condensing it. My first rule is log base b of, if I ever have multiplication within, I can actually break this apart into 2 different logarithms. I can break this apart into log base b of m plus log base b of n. These are actually based upon our exponent rules as well. And we'll go over those as well. We're just going it backwards because logarithms are the inverses, so they look slightly different than exponents. So an example of condensing one, hey, if I have log base 3 of 9 plus log base 3 of 5, I can actually condense them into one logarithm as long as they have the same base. Be careful and make sure they have the same base. So I locate the fact that we do have a 3 and a 3, so I can then condense it. I can condense this into, I want to show two of them. I can condense this into log base 3 of 9 times 5, which is just log base 3 of 45. But if I can condense things, I can also spread things apart. Now, in order to spread things apart, this needs to be a multiplication. Well, that can be up to you. How do you want to multiply numbers to get to 72? Realistically, you could use decimals if you want to, but probably look for things that make sense, like maybe 9 times 8 would be 72. Just find two numbers that multiply together. If they ask you to break it apart, you have to break it apart using our multiplication. All right. Real quick, what's the base of ln? E. Yep, it's actually log base e. It's just a shortcut to writing log base e because it's used so much with science that we call it the natural log. Okay, so we could actually break this apart into ln of 9 plus the ln of 8. Take a quick second and see if you can do the same things for 2 and 4. Log base 10 of 6 times the quantity x minus 3. Now that 6 needs to affect the x and it needs to affect the 3 as well. So we should have actually got to log of 6x minus 18. Make sure you had that 18 and you just have 6x minus 3. All right, if I'm asked to expand the next one, we have to realize it's got to be multiplication. Well, we needed to realize that this was a difference of two things. So I'm always thinking, is it a difference of squares? And if we look at x squared minus 4, well, 4 is a prominent 2 squared. It is a difference of squares. So this can be rewritten as log base 5 of x minus 2 times x plus 2, or x plus 2 times x minus 2. Doesn't matter what order they come in. Now we have a multiplication sign between it, so we can break those up into two logarithms. We can break this up into log base 5 of the first x minus 2 plus log base 5 of the x plus that 2. I think the hard part was just coming up with that multiplication one. Then we split it apart into two logarithms. All right, the only thing that changes in the next one is it's a quotient, so we're dividing. This is the way I always think about it, especially for exponential and these, they're kind of the same idea. If you're multiplying, we do something with addition to change it. If I'm dividing, we do something with subtraction to change it. So we're going to turn log base b of m divided by n. Now we're dividing, so instead of adding like we did up here, we're just going to go to subtraction. We're going to go, this is log base b of m minus log base b of n. So if I'm asked to condense things, I'm going to first make sure they both have the same base. They're both ln, so they both must have a base n. That means I can push those two things together, which will give me ln of 96, our first one, divided by our second one. The order matters. The order definitely matters because we are dividing. So the first one comes on top, the second one goes on bottom. We go ahead and do that division, and we would have, 16? If I needed to expand and I wanted to use the division property, I need to have division in here. Well, 8 isn't a division yet. I guess we could do 8 divided by 1 if you really wanted to, or you can get however you want to write it. So I'll just do log base 3 of, let's just do 16 divided by 2. That still equals 8. You could also do 8 over 1 if you wanted to. Now we do have a division, so I can split this apart into log base 3 of 16 minus log base 3 of 2. Try the other two. These can get a little complicated. Make sure you're careful with your power properties and stuff. So when we turn it to division, what happens if I have a power divided by another, like x to the 10th divided by x squared? Might happen. Real quick, we should have realized subtraction turns to division. So we should have said I can rewrite these because they have the same base as log base 7 of 8x to the 10th divided by 4x. I like that you're working, but I don't have to talk over you. Okay, but we can simplify this. We always want to simplify if we can. So I'm noticed we could do 8 divided by 4, which equals 2. So I can rewrite this as log base 7 of 2. X to the 10th divided by x squared. Either you know the property that it's 10 minus 2 gives you x to the 8th. Or you could just manually look at this. This is x times x times x times x times 8 x's. This is 2 x's. 2 of your x's cancel on both of those. You're left with 8 on top. All right, our last one was just breaking it apart. So we'd break this apart into log x minus 7 minus log x plus 1. And that is our quotient property. Last property is just your exponential property. Exponential property says, hey, if we have log base m and m is raised to a power, we can bring that power out front. This is the weirdest one. This is the most forgotten one because it just looks weird. That we can rewrite this as actually n times log base b of m. All right, so our first one says condense into a single logarithm. When I say condense into a single logarithm, you better not have any numbers out front. It better just be log base something of some number. That's what condensing means. So what we need to do to that 3 is we need to throw it in as an exponent. So we're going to have log base 10 of 6 cubed. Now we should simplify this. 6 times 6, 36, times 6, 180, 216. Can someone double check me on that? No. Okay, good. All right, we're going to quickly just do 10 together. We're going to go through these 4 together real quick just so we can release you into something else. If I have parentheses, I could take the entire in parentheses and raise it to that power. So writing this one equation will be ln of 4 to the x minus 1. And you're done. You can't simplify that. Expanding. Expanding just means that we need to get rid of any exponents we have. So in this case, we're going to take that x and bring it down in front. So this one's just going to be x times log base 2 of 5. The last one's a little trickier. Roots and exponents are the exact same thing. We just came up with this nice little way to show you what roots look like. But they are exponents. So whenever you rewrite a root as an exponent, you need to realize that this is actually ln of the 2x plus 1 raised to the 1/3 power. Whatever number's out here goes on the bottom of the fraction. Which means if I pull that out front, this is going to be 1/3 times ln of 2x plus 1. Are these. Because we never really formalized this stuff. We did a lot of lessons with it, but we never really formalized how I can write this or something that I can just look back for and look at this. So we're going to talk about exponential growth and decay and compound interest, which we just did. Exponential growth, it means something's getting bigger, which means it's got to be multiplied by at least 100%. So if I'm doing exponential growth our formula should be our starting value times 1 plus our rate. So if it's increasing 10%, it's 1 plus 0.1, and then it's raised to how much time you have. Decay is the opposite. If I say I'm decaying 10% every year, we have to be smaller than 100%. So if I want to decay, we're going to have A times 1 minus R raised to RT. If you need to go, you can go. For continuous, that was the one that we ended on. Continuous, we actually get rid of all of this. If it's doing it continuously, we do our A times that E that we came up with. I'm not happy with that. Yeah, that's what I wasn't happy with this. Because the A and E look weird. They usually change this to P. It means the exact same thing. P times E. It's the official one from like a book. It means the same thing as the A, your starting value. And then rather than raising it just time, it's rate times time. That's just if it's expanding or compounding continuous. You're looking for the word continuous to use the letter or the number E. Compound interest, we already talked about that before. Our compound interest is going to be our principal. So I am going to use P with this. It's the exact same thing as A. It's just our starting value. If we're compounding, we need 1 plus R divided by N. We'll talk about the N is in a second.
I have to go.
Where are you going?
For the musical.
Oh, okay. I got to go. All right, T times N. Where N is going to stand for the number of times compounded yearly. Of compounded yearly. That formalizes a little bit what we just did. That's what we did in the first problem where we had to put the N up here and N because it was monthly, so we had to put a 12 and 12 in here. Those are nice to just offhand know. You can figure them all out. We did those in those lessons, but sometimes it's just nice to have that formal thing that's written. And these are nice sheets. They're colored. We can keep them. We know that's where important stuff from this chapter. The only other thing I'm going to do is exponent rules really quick. I want to get to fractional exponents. I want to talk about fractional exponents. I don't think I put an example. We don't need an example. I'm just going to talk about fractional exponents because it's the one that most people forget about. A to an m divided by 2. Actually, let's go m divided by n is going to equal nth root a raised to the m power. We need that today. That's why I'm showing you that one specifically. The rest, I will post the solution key to this online if I haven't already, so you can go through it if you want to go through it. Otherwise, it's kind of up to you to fill it out. It's your sheet, not my sheet. I will put an answer key, but it's your sheet, and you fill it out when you want to. All right.